Alrighty, so we are now going to talk about the next topic of thermodynamics, which deals with gases. Usually in the book, this is discussed as the kinetic theory of gases. Basically, we want to be able to take a very complicated system like a gas. The reason it's complicated, of course, is a gas is made up of millions and millions of molecules. And each molecule moves in its own way under the laws of physics. And they could bump into other molecules. And so to be able to model a system which is made up of so many pieces is nearly impossible. To try to keep track of every single molecule, in which direction its velocity is going, what would happen if it collides with another one, when will it collide with another molecule, how will they reflect off of each other, all this kind of stuff is just, it would take so much computing power that we just don't do it. Or at least we're not yet at the point with computers to be able to really handle such loads. But we still need to be able to model how these systems work if we want to be able to predict what would happen or answer questions or things like this. And so what physicists usually do when they run into a problem where they need to figure out something about the real world, but the real world is too complicated for us, we make models, approximations. We say, okay, I may not be able to give you exact answers, perfect, exact, as if I'm God. However, if I forget about the fact that there are certain complications which are there but maybe won't make that big of a difference, then I get rid of a lot of the complication without losing much information, and I can still get an answer from a prediction that's at least fairly close to what the perfect answer would have been. And of course, we've been doing this in physics all the time. When we talked in first semester physics, we discussed, if you shoot a cannonball off at an angle of 30 degrees with a velocity of 20 meters per second, how far will it go? Well, we didn't discuss, number one, air resistance. How would air resistance affect how far the ball is going to go? We didn't affect drag or the shape of the ball. How does the shape of the ball affect the drag? We didn't discuss whether the ball would be spinning when it came out, and if a spinning ball would move further than a non-spinning ball. Or we didn't talk about the curvature, or not the curvature of the Earth, but that could be a thing, but also the spin of the Earth, the rotation of the Earth. If we shoot a cannon to the east versus shoot a cannon to the west, the fact that the Earth is rotating means the ball would go further in one direction than the other. All these things we didn't take any account of whatsoever because they would make the problem much more difficult. Yet, we're still able to get a fairly accurate answer by taking a more simplistic model. Maybe we're off by a few centimeters in our calculations, but, if we could get within a few centimeters by not having to worry about hundreds of hours of computing time to try to figure out realistic answers, it's a good trade-off. And so all of this is to say, what we're going to discuss right now is an approximation. It's a model, and it's called the ideal gas law. And that's exactly why it's named this. It's because we're going to assume things about the gas that we discuss, that we have problems on, which may or may not be true, but if they were true, then the gas would act the way this model says. And if they're not true, then maybe the true gas wouldn't act the way the model says, but maybe it'll act close. It'll be similar. And of course, in real life, if you have a system that's really far away from being an ideal gas, then we'd have to come up with a different model for those things. But for the purposes of what we're going to do in this course, the ideal gas law will be perfect for us. It'll be able to handle the types of problems we want to discuss. So, of course, first thing I should say is, what is the ideal gas law? What is this equation? It's a famous equation, and it actually has two different forms. Both of these equations I'm about to write down are called the ideal gas law. It just depends on how we want to discuss the gas, and I'll explain that in a little bit. First is P times V equals N times R times T, where P is pressure. Of course, the units of pressure are what's called pascals. PA, Pascal. A pressure can be thought of as like, how much force does this gas exert on the wall of the container it's in? The pressure of the gas. How much force is it pushing per area? And so that's what a Pascal is. Pascal is Newton per meter squared. Newton per meter squared is the units, and we call a Newton per meter squared a Pascal. It's force per area. V, capital V, that's the volume. So if we have some amount of gas and we put it in a container, the gas, one of the features of a gas is that it always fills the container. So no matter what container I use, the gas is going to fill it. So if I have a very small container or a very big container, it doesn't matter. No matter what the shape of the container is, the gas will fill this container, and thus we call the container it's in has a certain volume. The units for volume we're going to use are cubic meters, meters cubed. Now, one thing to note is, there are other subjects that use ideal gas law, chemistry being a significant one. And sometimes, if you're not using the metric system or you're using some other system of units instead of what physics is going to use, you may see liters, you may see cubic centimeters, you may see milliliters. All of those are units of volume. For the physics course, we're using cubic meters, meters cubed. All right, N, little n, is the number of moles. Now, we need to discuss what a mole is. A mole is a descriptor for a certain number of things. So just like you may have, when you go to the bakery and you get a dozen donuts, a dozen stands for the number 12. If I want 12 donuts, I can say I want a dozen donuts. It means the same thing. It's just a different word for this set of 12 things. We call it a dozen. Same thing for a mole. A mole is a certain set, a set of things of a certain number, and the number is 6.02 times 10 to the 23rd. That's a very famous number. It's Avogadro's number. So if you have a set of objects and you have 6.02 times 10 to the 23rd of them, then you could say I have 1 mole of that object. So it's just a fancy term. It's useful in the ideal gas law and thermodynamics because, like I said, when we're discussing gases, we're discussing sets of molecules which have such a high number of molecules in them that, if we tried to count how many, it would be hard to count. If we tried to say, oh, it's, a billion dozen, that's just stupid to say. But instead we could say there's 3 moles or a half a mole. Well, that's a much easier way of relating how many objects there are. So that's basically telling you how much gas you have. As I said, trying to say, oh, I've got a gallon of gas, not gasoline, but a gallon of oxygen gas, that's telling you a volume. I have a gallon container and I put oxygen gas in it, but that's a bad way of saying how much gas you have. And the reason is because if you have 5 molecules of oxygen gas and you stick it in there, it fills that gallon container. If you have 5 bajillion molecules of oxygen gas, you could put it in a 1 gallon container too. So trying to tell me you have a bucket of oxygen is a bad way of saying it. But telling me how many molecules you have, how many moles of oxygen you have, that's good. Now I know how many molecules you're talking about. So that's what the little n represents. How much of the gas are we describing here? Then there's this R, and R is the universal gas constant. And just as is usual in physics equations, because we're using a certain set of units that has nothing to do with the actual universe, it has to do with human beings, the numbers won't come out right unless we stick in a factor to make the numbers work out correctly. And here, this is an example. We have to stick in this number so that we get the right answer when we use our equations. And what is this number? Well, it's actually fairly easy. It's 8.314. Very nice. Easy number. Not big like the Avogadro's number. It's a nice, simple number. It's got pi in it, which is pretty cool. Not exactly pi, but close to it. And then finally, there's T. And of course, this is thermodynamics, so you can guess T stands for thermometer, not thermometer. Stands for temperature. Now, I hope you're already saying to yourself, here's a physics equation that depends on T, but does not depend on the difference or the change in T. Yes, this has to be in Kelvin. So if you get a problem where you have to use ideal gas law and it gives you the temperature in Celsius, convert to Kelvin. You must be in Kelvin for this to work. So there's the ideal gas law. What does it relate? It relates all of the different characteristics about a gas that may be important. How much gas do you have? That's the number of moles. How hot is it? That's the temperature. What kind of container is it in? Is it in a very small container or a very large container? That's the volume. And of course the pressure, which may be dependent on these characteristics. There is a secondary form, which I said at the beginning. There's 2 ways of writing it. The second way of writing it is very similar, PV. And here's the change. Instead of little n, we have big N, and instead of R, we have little k. So what's the difference between the first and the second? Well, instead of moles, big N is the number of molecules. So if you're told, it's got 5.03 times 10 to the 28 molecules in this gas, and you don't know the number of moles, then you'd probably want to use NKT instead of NRT. And of course, instead of the ideal gas constant, R, since we're talking about molecules instead of moles, we use Boltzmann's constant. Now, this is not Stefan Boltzmann's constant, which we saw in radiation. This is a different one. This particular constant, K, is 1.380 times 10 to the minus 23rd. Okay. So, here we have the 2 forms of the ideal gas law. They're the same thing. It's just if you don't know the molecules but you know the moles, then you use the first one. And if you don't know moles but you know molecules, you use the second. All right, so As I said, what this does is it models the behavior of a gas and it relates its characteristics to each other. Because if you think about it intuitively, physically, if you have a gas, let's say you put this gas into a container, okay, it's sitting in there. If you start to heat up the gas, raise its temperature, what happens to the molecules of the gas? Well, let's kind of look at it. Here's our container. And we have gas molecules in here. And I put a fire on. As you can see, I'm a great artist. What does this do? This heats up the gas. What does it mean to heat up the gas? You're making the molecules of the gas vibrate faster and faster. And so what winds up happening is these gas molecules start to move very fast and start to collide with each other and with the walls of the container. Because they're moving very quickly, they start to bounce off the walls very hard. And what happens to the walls is they feel this kind of outward pressure building up. Because overall, you've got these molecules busting around the inside of the walls, trying to push the walls away as they reflect, as they bounce off. And the faster they move, the harder they hit the walls. So what this tells me is if I increase the temperature and I'm keeping the gas in the same volume, in the same container, then what must happen is the pressure has to build up. So that means the pressure depends on the temperature. As the temperature goes up, so does the pressure. And of course, the same in reverse. If I cool down a gas, those molecules start to slow down. They don't hit the walls of the container as hard, so the force on the container is lower, so the pressure goes down. And what you're going to find is when we use ideal gas law, what we tend to do is use a piece of this equation. So that's what I did here. Notice that I'm keeping the volume constant. Of course, I keep the same number of molecules, and R is a constant for this particular example. So the only thing that could change is the pressure and the temperature. Thus, I have a new equation, if this is true, under the assumption the volume is constant. Then we have a new equation that says P is proportional to T. As temperature goes up, pressure goes up. A fancy way of writing this, like a good equation, is P1 over T1 is P2 over T2. This is a very, very interesting equation. In fact, it's got its own name. It's called Gay-Lussac. I don't know if I'm saying it perfectly correctly. But this form of the ideal gas law, where volume is constant, the Gay-Lussac equation, is a good equation when you have a problem that's something like this. You have a gas, an ideal gas, who's at atmospheric pressure, who's at some pressure. You increase the temperature from 30 degrees up to 80 degrees. What will the new pressure be? Well, note, you know the original pressure, you know the initial temperature, and you know the new temperature, so you'd be looking for P2, the new pressure. All else being equal, then if you change the temperature, you'll change the pressure, and vice versa. Of course, it's also true that if I take this container with gas in it, and I somehow find a way to change the pressure. How do I change the pressure? Well, let's just say I make the pressure go down. What is that telling me? That means the molecules were hitting the walls with a certain force, and now they're hitting the walls at a lower force. The only way for this to be true, given the volume doesn't change, is that the temperature had to go down. How do I know that? Because if the molecules of the gas are the same molecules, the walls aren't moving because it's the same volume, then the only way for the molecules to not hit the walls as hard is if they're not moving as fast. And if they're not moving as fast, that means they have a lower temperature than before. So this is one form of the ideal gas law, where the volume doesn't change, but only pressure and temperature. Of course, there's another form. What if instead we have something like this? Take a canister. Let's say instead of a canister like that, what I have is a little piston. And again, I've got my little gas molecules in here. Now note what I have here. I have a can of gas, like some gas, nitrogen, oxygen, I don't know what it's made of. Let's say it's an ideal gas. And on top, instead of a lid, I have a piston. And this piston I can push down, lower it into the gas, or I could raise it out. But it's a piston that is like, there's no way for the gas to escape. So if I push this piston down, all the gas eventually must be forced down. So that now all the gas is in this little bitty space down here. Okay? So I went from this first step to the second step. What did I do? I pushed my piston, compressing the gas into a smaller volume. Well, let's say I do it in such a way that it's in this background. So I have it in like this container that can soak up excess heat. So any heat that gets built up in the gas that's more than normal gets sent out of the gas and into the environment on the outside. Okay? If I can do it that way, then what am I doing? What I have is this. I have a gas that's at a certain pressure, in a certain volume, and at a certain temperature. Okay, so let's call it P1, V1, and T1. Then I do something so that now my new gas, same gas as before, but now it's in a much smaller volume, but I leave the temperature the same. I can ask what happens to the pressure. Well, first of all, if the temperature didn't change, then I could forget about all about the temperature. It doesn't matter. So if the pressure and the volume of the gas are here in the first step, I lower the volume into the second step. What happens to the pressure? Well, look at the ideal gas law. PV equals nRT. First of all, what do I know? All of these things are constant. They don't change, right? The number of molecules is the same. They're not escaping. R is just a number. And I was told that the temperature doesn't change. As I squeeze the gas, if there's any extra heat, it just leaves. That's what I'm forcing it to happen. So if all of this stuff is just a constant, let me call that constant alpha, just to have a name for it. P times V equals alpha. So if P1 times V1, the original state, is equal to alpha, but alpha is constant, it doesn't change, and that means in my second state, P2 times V2 must also equal alpha. But if this thing's alpha and this thing's alpha, that means this thing must equal this thing. Right? If A is equal to B and C is equal to B, then A must be the same as C. They're both the same as B. So, what does that tell me? P1 times V1 equals P2 times V2. A new equation. Under the assumption the temperature doesn't change, that's called isothermal, we have a new identity, which is called Boyle's law. And it relates the pressure to the volume. What happens if I change the volume of a gas, leaving the temperature the same? Well, if I lower the volume, notice what's going to happen. If I lower the volume, I'm compressing all that gas into a much smaller space. As I'm compressing, these gas molecules start to hit up against each other harder and harder and harder because I'm pushing them together myself. And of course, they not only hit up against each other, they hit up against the walls. So as I compress, I'm making them move faster. They hit off the walls harder than before. The pressure goes up. If instead I release the piston and I let the piston go back up, then those molecules will start to slow down. They won't bounce off each other as fast, and thus they won't bounce off the walls as quickly, and thus you'll have a lower pressure. And of course, this opposite you can tell. What happens if I have this little piston is free to move? It can move freely. If I increase the pressure of this gas, then those molecules are going to hit on that piston very, very, very hard. That's going to make the piston want to rise up. And so you'll change the volume. You'll increase the space, the volume, for this gas to live in. So if you increase the pressure, you must be increasing the volume. You must try to increase the volume. Once the volume increases, though, you lose that pressure. You've used it up. Okay? So Boyle's law relates pressure to volume if the temperature doesn't change. Well, obviously, there's another. And this is very similar. You have a container. You have your gas in it with a piston lid. You push down on the piston. What happens? You now have your molecules. Well, obviously, if we don't allow the heat to escape, as I push these molecules down, they get faster and faster and faster, like before. And so just as they would increase the pressure, let's pretend like we don't care about the pressure. All we want to know about is the temperature. Obviously, the temperature should increase. Because again, as I compress this gas into a smaller space, those molecules start to hit up against each other faster and faster, and so the temperature should go up. So we have V1 over T1 is V2 over T2. How does the volume affect the temperature? Through this equation, which is known as Charles' law. So all of these things are coming from the ideal gas law, PV equals nRT. This first one, if we let the volume be constant, then we have an equation that relates pressure to temperature. The next one, if we allow the temperature to be constant, pressure and volume are related. And of course, with Charles' law, if you allow the pressure to be constant, then we relate volume and temperature. One last thing to talk about is don't memorize all of these equations. You only need two. PV equals nRT. That's the big guy. The one I would remember instead of these three I just talked about, Boyle's, Gay-Lussac, and Charles, remember this one. P1 V1 over T1 equals P2 V2 over T2. Now, why should you remember this one instead of those other three? The reason is because this one tells you the other three. For instance, say I give you an equation or a problem, and I say, if you increase the pressure, what happens to the temperature, letting the volume stay the same? We'll just say, okay, forget about V. Since V doesn't change, V1 is the same as V2. You can take them out. So what's left? P1 over T1 equals P2 over T2. Or if you have a problem where I say let the pressure be the same, I don't tell you anything about the pressure, but I'm changing the volume and I want to know what happens to temperature. V1 over T1 equals V2 over T2. Or temperature is the same. If I increase the volume, what happens to the pressure? P1 V1 equals P2 V2. You see, all three of those other ones come from this big one. It's just that the big one has all three components, pressure, volume, and temperature. So when you're given a problem, if the temperature is not changing in the problem, then take this big one and just don't write the temperature part of it. So you have P1 V1 is P2 V2. Or if you have a problem and the volume doesn't change, keep the volume away. So you have P1 over T1 is P2 over T2. So there's only two you need. Ideal gas law and this universal guy, this big one. The other ones come for free with it. So next video I'll have some example problems where we work some of these types of problems where we use these. But you can see these equations aren't that difficult. These are going to be problems where I basically give you all the information, all the numbers. You figure out which of these equations you need to use and just plug the numbers in and solve for whatever the unknown is. If I tell you the pressure was originally this number and it got up to this number, the temperature started here, what's the new temperature? Obviously you're looking for T2. So you'd say P1 over T1 is P2 over T2, solve for T2. These are going to be fairly simplistic problems, but they're important. And the best way to be able to handle the problems is to understand these characteristics intuitively. In your mind, if I told you you have a container with some gas molecules in it, and a container is closed, if you heat up that container, what's going to happen? Well, it's easy to tell. Number one, as you heat it up, if the volume can't change, the pressure goes up, right? That's what P1 over T1 is P2 over T2. If you started with a certain pressure, you started with a certain temperature, now this guy goes up, well, what must happen to him? Well, look, P2 is P1 over T1 times T2. So if T2 is bigger than T1, P2 has to be bigger than P1. So pressure 2, the new pressure, is going to be much higher. So that means the gas pressure will build up in this container. Well, what's going to happen if the pressure builds up? The thing's going to explode, because eventually that gas does not want to be in a small container. It wants to increase its volume. You're forcing the volume not to change, but it wants to change the volume. Eventually that volume is going to go up. But until that time, if you have a closed container, the pressure is going to build. I mean, intuitively, you understand that. I mean, you can tell. You stick a can of Coke, you put it on a campfire, the thing's going to burst. Why is it bursting? Because gas builds up in the container. Let's say, even if it's a thing of water, the water will eventually boil, turn to steam. That steam will continue to heat up, get into very, very high pressures until it busts out of the container. Thankfully, you have that intuition. Just apply the intuition to these characteristics. If I compress a cylinder of gas, will the temperature go up or will it go down? Here's a nice little thing. I don't know if you've ever tried it, but if you've ever had one of those cans of air that you use to clean off a keyboard or things like that, what happens to the can as you spray that air, that pressurized air out of the can? If you hold on to it for a while and you keep spraying it, eventually something happens to the can. What happens? It gets cold. Why does it get cold? Well, look at these characteristics and tell me. What did you do? You had a certain amount of gas in the container. You released some of that gas. So now there's less gas in that container. It's as if the gas is now in a bigger container because there's more room for the molecules. If you increase the volume for the gas, you lower its temperature. So as you release the pressure, as you release the gas from the pressurized container, the gas feels as if it's now at a higher volume. It's not as pressurized. There's a lower pressure. If you lowered the pressure, you've decreased the temperature. So it got colder. These types of things, now you can see why they happen in real life. But anyway, next video we'll have some example problems we can work on and see how to use these. But for now, this is the theory you need to know. So until next time.